All right, so today we'll finish the curve metric and begin, I guess, more contemporary topics in the sense that things that have been done over the last 10, 15 years and not long time ago. And in fact, with the next lecture and the following lectures, we'll do things that were actually, a lot of them were actually done here at Penn State by students and postdocs. So that will be exciting. Okay, so last time we sort of we finished the we finished the global analysis of curved spacetime using the using Gaussian metrics, and so we're doing this. What we did was the topic number 5, which was singularity structure. And then we use the Gaussian form, the metric, and then we began the interplay between geometry and physics. In curve code, so we'll continue now. So let me remind myself where exactly we were at. Yeah. So we wrote down the Boyle-Lindquist form of the metric. Here we began by writing down the Boyle-Lindquist form of the metric. Which is sort of like the generalization of the Schwarzschild coordinates, metric and the Schwarzschild coordinates. It's long and boring, but we are going to need some facts about that metric. Therefore, I'll write it down again. So this is going to be given by dA squared is equal to the norm of the Killing vector, delta minus a squared sine squared theta, 1 sigma dt squared minus 2 plus 2 sine squared theta times 1 squared plus a squared minus delta 1 sigma dt5 and then plus r squared plus a squared whole squared minus delta times a squared sine squared theta divided by sigma multiplied by sine squared theta times d5 squared plus sigma delta dr squared plus sigma theta squared, where delta is r squared plus a squared minus 2r, and sigma is r squared plus a squared plus squared theta. So in the Schwarzschild limit, a goes to 0, and b just goes to r squared times 1 minus 2a for r, and in the Schwarzschild limit, d just goes to r squared. So what we saw last time was the following, that this of course is dt squared term. First of all, by inspection it's clear that the metric coefficients do not depend on t or phi. Therefore, it is again true that d by dt and d by d phi are Killing vector fields. In Schwarzschild spacetime, we had 4 Killing vector fields. We had time translation, d by dt, but we also had 3 rotations. Now there's only 1 rotation because there's explicit dependence on theta here, which we did not have in the Schwarzschild spacetime. So it's not spherically symmetric, but it is stationary, d by dt, and is axisymmetric because there is d by d phi. Of course, in the limit in which a goes to 0, a is the angular momentum parameter. So as I said ahead of time, a is going to be the angular momentum per unit mass. So A is angular momentum parameter. So as A goes to 0, we get Schwarzschild's metric from here. That's what we saw last time. Now there are some features of this metric which are sort of important. This is geometry and which has direct effect on the physics. The first feature is that in Schwarzschild spacetime there was no cross term dt d phi. As we will see today, and also in your homework, the second homework is going to be due not this Wednesday, but a week from this Wednesday. It is on the web page and the announcements. So in the homework that you'll see that in this case what happens is that the fact that the dt d phi term is not 0 is directly responsible for the fact that the vector field d by dt that we have is not really perpendicular to any surface. And we're going to study this in a little bit more. At the moment, just accept this, that d by dt is not, in Schwarzschild spacetime, d by dt vector field was everywhere perpendicular to t equal to constant surfaces. Here, because of dt d phi, it is certainly not this term, because of this term, it is not perpendicular to the t equal to constant surfaces. It has a part in the t equal to constant surfaces projection. But more importantly, that you cannot draw any surface such that it is everywhere perpendicular to that surface, any space like any surface to which it is perpendicular to that surface. And also because I got this d phi, whatever is true for t is also true for phi. So in Schwarzschild, d by d phi was also hypersurface orthogonal because it is a spherical symmetric, so you can just draw a surface on which to which phi would be orthogonal, right? I mean, just look at phi equal to constant, then it will be perpendicular to that. Whereas here, the statement is that this vector field d by d phi is also not hypersurface orthogonal. The fact that they are not, the fact that d by dt is not orthogonal to any space-like or any surface, in particular, we would like it to be orthogonal to space-like surface because the Killing vector field was time-like at infinity. But the fact that it's not orthogonal to any surface is related to the fact that there is rotation in space-time. And this is what we will explain in a minute today. So, as I explained last time we also did the conformal completion using the Kerr-Schill form. Again, we can just use conformal factor to be equal to 1 upon r, and you can use chart ur theta phi. So these are like Eddington-Finkelstein coordinates, or so this will give you sky plus conformal completion. Or you can use VR theta phi, Britain's coordinates, and this will give you square minus. I've drawn those pictures several times, so I'm not drawing it again. These two, what these two charts do. So the picture that we had was really that I got, again, these horizons, because I got scry here. So this is scry plus. This is u which is equal to infinity. This is u equal to minus infinity on scry plus. This is v equal to minus infinity. This is v equal to infinity. This is sky minus. And we see that the path of all of this sky plus sky minus is not all of space-time, but in fact it stops at this horizon, at which this delta vanishes. So if I look at this in the Schwarzschild limit, when delta vanishes, that is the horizon, r equal to 2m. And the same thing is true here. When delta vanishes, we actually get this horizon up here. And you can look at the roots of this equation, delta equal to 0. I think we saw that last time. And we get two roots, r plus or minus is equal to m plus square root of m squared minus a squared. And therefore, the two things are, so that this is where this r vanishes. So the two things that are immediately follow from here. The first is that if in fact m were smaller than a, then there would be no horizon. And then the singularity therefore would be naked. The first thing that follows is that if m is smaller than a, if there is mass if the angular momentum is very large compared to the mass, if you like, then so in the physical space-time, it's of course real manifold, real space-time, the horizon, it doesn't exist, this surface doesn't exist, and then we have got naked singularity. Singularity is visible. I'm not drawing the whole Penrose diagram for that. I'm just stating it at the moment, then the singularity would be actually visible from infinity. So the black hole interpretation requires, if and only if angular momentum is a parameter smaller than mass, angular momentum J is smaller than m squared. So that is a statement, first of all. We're always using units in which, most of the time, in which all the time when the speed of light is equal to 1, and most of the time when the Newton's constant is also equal to 1, and therefore it turns out that angular momentum has the same dimension as mass squared, and therefore A has the same dimension as mass, and mass has the same dimension as length. So we're using the units here. I can put G equal to, restore G everywhere without, it's very straightforward, it just takes more work. Restoring C is a little bit painful because the metric coefficients have C in one term and not in C in other terms, so it's not just overall things, so we have to be a little bit more careful. But we are putting G equal to 1 and C equal to 1 for most of the time. And then for the statement is that mass has the same dimension as length, has the same dimension as an angular momentum, has dimension of mass squared or length squared. Okay. So now, so that is the first thing up here. And then the second thing is, second notable thing about R plus minus, this formula up here, is that you see that in the A equal to 0 limit, R plus and minus coincide, and that is equal to 2m. But if A is not equal to 0, then this quantity is always less than 2m. So angular momentum actually shrinks the horizon, if you like, because it is not at R equal to 2m, but R equal to something between m and 2m. So that is the first remark, and the second remark is that if A is not equal to 0, the horizon, the outer horizon up here, R plus, is less than 2m. Okay, so it's doesn't. So now what we would like to do is, so this is the region 1, and I was just saying that, well, this is also region 2. But now, if you go inside, what happens? Well, in Schwarzschild, you went inside and you got R equal to 0, and that was a singularity. But here something new happens. Namely, now what happens is that as you go inside, before reaching R equal to 0, you are going to reach R equal to R minus. That is to say m, plus minus. So R minus, that is to say m minus m squared minus a squared. And there again, the norm of the Killing vector field, there again it will be the case that you'll get a horizon again. And this horizon, therefore, the picture therefore you get is really, this is R equal to 2m. So this is R equal to R minus. So this is the inner horizon. And then if you decrease, so the same thing will happen here, R equal to R minus. This again is going to be. And on this side again, you can conformally complete, and you can attach sky. So you get sky plus here, sky minus here. It's completely parallel to what was happening here. I'm erasing these points because this point is when v is equal to infinity, u equal to minus infinity, and infinite values of coordinates are not part of the manifold, and therefore these points are not here. Okay, but here I get R equal to R minus, R equal to R minus. And then you can continue to decrease further, and then you'll hit the naked singularity. So the picture that you would get is really, if you continue to decrease this, then again you will get a naked singularity up here, which will be not naked singularity, the singularity, which is of course protected by the horizons. You will get here r equal to 0 and z equal to 0. So you will get here this line of here. So I want to emphasize one thing that I should emphasize right away, that in the Schwarzschild space-time, when we drew these pictures in Schwarzschild space-time, then I have the picture like that. This was a singularity, and these were the horizons, and this was singularity, and this was the picture that we had. This is the picture we had. Each point up here, except for r equal to 0, was a two-sphere in Schwarzschild space-time. In this case, that is not, because I do not have spherical symmetry. Therefore, the picture depends on the value of theta. It doesn't depend. It's not independent of theta, and therefore, what we're doing here is just one value of theta, and I'm looking at theta equal to 0 slice. So each point up here is really a point at theta equal to 0 is like the north pole of the sphere. So it is just the north pole of the sphere, and then I got r and theta and r and t coordinates up here. So this really is not the same footing as here, because here everything is a point. Here everything just depends on this particular value of theta, and we're just choosing theta equal to 0. Of course, you can just take the metric and plot other values of theta. We're taking this because it's the simplest to draw. And then, therefore, I'm going to get here. A singularity. This really is a ring singularity, but its projection on this plane, or on this theta equal to 0, this two-dimensional surface, is just going to be a line, r equal to 0. And therefore, I get this singularity up here, and then again, this singularity is going to be continued up here. So the space-time diagram is much more complicated. The same thing happens up here. The singularity in this case inside is actually time-like, as the picture indicates. These are all Penrose diagrams. In these Penrose diagrams, I got light cones which are at 45 degrees. This is important to remember always. And then whatever is inside the light cone is time-like. Whatever is outside the light cone is space-like. And light cones are always at 45 degrees. So therefore, you get this singularity whose structure is complicated. But of course, for our astrophysical purposes or practical purposes, all these inner regions are not that important. Really, we would like to focus ourselves on the region 1. And what happens is that, so we can have, just like in Schwarzschild case, these regions, the regions 1 and 2, and then we got 3 and 4 up here. We could only focus on region 1 and part of region 2. For example, in the stellar collapse, I got a collapse like that. Then I got a singularity formation. And then the picture that is of interest is here. Here is a star at any given instant of time. This is the solid ball is a star. This is time running up here. This is r equal to 0 singularity. And this is our horizon. It separates a part of space-time from which is visible from sky from the part which is not visible from sky. So this is what is happening. So similarly, these extra regions, analytical continuations, of course they exist for the curve solution. And in mathematical calculations, you should consider them. But the statement is that physically, they are not that important. I just want to say just one fact that I would like to tell you. That what happens is that if you give yourself initial data here, so for example, if this is curve space-time, and I would like to put some matter field on it, like for example, Maxwell field or scalar field, or a linearized gravitational field, or even a nonlinear gravitational field. In other words, I would like to go away from curve space-time in a little neighborhood of curve space-time. So I give here data which is close to the curve data, in a nonlinear case, which is close to the curve data but is not curve data, and then I evolve what happens. Well, then I'll get a space-time, and what happens is that, in fact, the perturbation tends to diverge. So therefore, these are unstable under perturbation. And so physically, or generically, these horizons are not reliable in the sense that perturbation would actually diverge here, and the singularity structure would change. This is an active, for the linearized case, these things have been understood quite well. But in the nonlinear case, we don't fully understand it. There are hard results in the case when, in the Reisner-Nosdorf black hole, the charged Schwarzschild black hole, which is spherically symmetric, but which also has an inner horizon, and one sees in their explicit calculations that these inner horizons are unstable. So these horizons are really unstable up here, so we don't trust what is happening beyond that in a generic situation. So this is kind of the global picture. I know I'm being sketchy, I've not derived things, but I think the derivations are rather detailed, and you won't need them. You just need to know the physical intuition. Again, if anybody wants to do a term paper on this, I can give the reading material and write down and also give you some references. As a separate announcement, like today or tomorrow, I'll put one separate announcement in which I'll put topics for term paper and also references, and it will be just cumulative, so you can take a look at it whenever you want. Again, the term papers are not long; they're between 5 and 10 pages. But what I need to see is that you really understood something and not just copied from some sources, but your take on that particular topic is what I would like to get. Okay, so this is the global picture of the Kerr space-time that one obtains. Again, what we saw last time was this singularity is really a ring singularity. The global structure of space-time is much more complicated than Schwarzschild space-time. But for all practical purposes, I think most of the time we're going to stick with this region, and sometimes the inside region, but really in the exterior region of a black hole, outside the horizon, that is to say the region which is visible from infinity, what are the physical manifestations of the Kerr geometry? That is what we're going to see from now on. Yeah.
So why does that behavior happen for the inner horizon, if you want to say intuitively? It's a Cauchy horizon, I think, right?
Yeah, it's a Cauchy horizon. It is because of the piling up of the because of blue shift effect. The energy just piles up on these horizons. I think the intuitive understanding of it was really given already by Penrose and Floyd in the case of Reisner-Nosdorf solution in the 70s, long time ago. And that paper is is good to read, not because it is definitive by any means, because it is all kinds of approximations which are made which are not realistic. But on the other hand, you understand the physical reasons there. And those physical reasons are really borne out in this detailed analysis. The detailed analysis for Reisner-Nosdorf, if anybody wants to look at it, was done by the Formos, DE. So the first paper was Penrose and Simpson. It's a very old paper. It will give you sort of intuition as to why the inner horizons are going to be unstable. Penrose understood it very early on, and then more detailed works now. And there were sort of many papers in between, I should say. There was papers particularly by a group of Werner Israel, Eric Poisson, and various other people. But the kind of a very definitive paper is by the Formos. And these are all, however, for charged Schwarzschild. Reisner-Nosdorf. They're still static, but as is generally regarded as being kind of a simple model for Kerr space-time. Simpler model for Kerr space-time. I think Wheeler called it something like poor man's Kerr space-time. It was supposed to, it has similar global features, but because it's spherical symmetric, it is much easier to analyze, and the expectation is that the qualitative conclusions we draw about this Reisner-Nosdorf are also true then. Any other question? All right. So this is just elementary curve, and now what we're going to see is the more detailed thing about geometry and physics of Kerr space-time. So, as in the case of Schwarzschild space-time, the interplay between geometry and physics is really brought out by looking at the symmetries of space-time. I mean, not all the interplay is related directly to the symmetries of space-time, but properties of the symmetries really bring out very deep physics. So that's what we're going to do now. Are there any questions? Yeah.
So previously you said that like for ring singularity, usually speaking, you could go straight from the top to like through and then to the other side. If the r minus are unstable, does that mean that like I can no longer do this? And, like,
Right. So you're not even reasons ring singularity. You'd already the singularity will be here.
Mm-hmm.
The generic singularity is likely to be null rather than space-like, and is likely to be this accumulating on these three-dimensional null things rather than. So I think the general belief is that the generic singularity will be really null, and piling up on these Cauchy horizons or on these inner horizons up here. That is where the generic singularity will be. It will be quite different in the real world, so to say, rather than in this idealized space-time. By real world, I mean any kind of perturbation of Kerr generically will lead to that behavior. Again, this is for Kerr, not completely established, but that is a general picture on that.
Is there any reason to think that there won't be a singularity if there's a nonlinear perturbation? It's completely gone, or?
No, so there's no reason to think that, because I mean, we see. Okay. This goes back to our question about what is a singularity, right? This is what we're doing, right? What do you want to? So, if we want to say that the space-time is regular, if in fact the metric is actually C2, so the curvature tensor is well defined, and Einstein's equations are imposed in the standard sense, not in some distributional sense, then the statement is that already Rice-Nosdam behavior tells you that the singularity persists. That is to say, there is actually a curvature singularity. Now, in the high mathematical literature of geometric analysis, there is a lot of debate about it. If in fact the metric is only C0, if I had this C0 extension, should we call it a singularity? Because I can extend the metric in a continuous fashion. But of course, that means that the Christoffels are already singular, or the derivative operator is already singular, and therefore the wild tensor is also singular. So everybody agrees that the wild tensor is going to be singular. The question is whether the fact that I can continue across it in a distributional sense, should I regard it as a singularity or not? So these are the questions that are debated by various communities. I think the physics take on it is generally well. If the curvature blows up, then in fact you're going to be torn apart, and that's a singularity. But then people come and say that physically this is what is going to happen to point particles, because this is geodesic deviation equation. But in fact, in real world, what we have is fields. And the key question is, can I propagate fields across it? And then it comes to what kind of fields? And then there's classical fields and quantum fields. So we get into a bunch of complications like that. But if by singularity we just mean that the curvature tensor blows up, then no. Then the statement is that you cannot extend. This is the end of it. Of course, what happens in quantum gravity is altogether different, because then Einstein's equations are superseded. And there are new effects that can be brought in by the extra terms, and then the singularity can be resolved, and that is the general hope. All right. So now we'll really start with the second part, which is the geometry and physics. So we look at Killing vectors and their properties. So as we already saw, that there are two Killing vectors, d by dt and d by d phi. And what you call these Killing vectors, how do you interpret these symmetries, is all determined by what happens by what these Killing vector fields do at infinity. Because we take then our intuition from Minkowski spacetime. So we look at this d by dt and d by d phi. And if you went to Kerr-Schill coordinates, that we did in great detail, then in fact d by dt really goes to d by dt, the Minkowski Killing vector, the Minkowski time translation, and that's why we call this d by dt stationary Killing vector field, or time translation Killing vector field. And more precisely, it's also true that if you just look at the norm of this Killing field, This is now the Killing field. As you go to infinity, see what happens. I got here sigma, and sigma goes like r squared. Sigma goes like r squared plus, so at infinity is the dominant term is r squared up here. I also have here delta. Delta also goes like r squared plus a squared. So the leading term at infinity is r squared upon r squared. Therefore, the norm goes to -1. So in particular, the norm goes to -1 at infinity. And this is again compatible with our interpretation that it is a time translation like Killing vector field, because we are interpreting it with what happens at infinity. We saw this already in the case of the Schwarzschild spacetime. The time translation Killing field was called time translation because it looks like a time translation at infinity. In fact, near the horizon, it looks like a boost in Minkowski spacetime. But we don't call it a boost Killing vector field. We call it a time translation Killing field because that is the convention there. Because we classify Killing fields according to their behavior near infinity, where the metric is approaching the flat metric. And d by d phi similarly really approaches the d by d phi of the Cartesian coordinates of the Kerr-Schill form, and therefore this is the z directional rotation. It approaches z directional rotation in Minkowski spacetime. So in our Kerr-Schill coordinates, it really becomes x dy minus y dx in the Kerr-Schill spacetime, and therefore this is the therefore this vector field is called rotational vector, rotation along z-axis at infinity. So these are the interpretations. But this is just a little exercise. It's like 2-line exercise, but I still ask you to do it. In fact, this vector field that I got, d by dt, the norm of this Killing vector field is this. So the norm of GAB, TATB is just GTT, which is just this, and that is minus delta minus a squared sine squared theta upon sigma. And the homework asks you to check explicitly that already on the horizon, on this r equal to r plus surface, this quantity becomes positive. So this is bigger than 0 at r equal to r plus. So that means that the Killing vector field TA is actually space-like. The horizon. It is not really time-like at horizon at all. We call it time translation, but it's not even time-like at the horizon. Near the horizon. In Schwarzschild spacetime, this d by dt Killing vector field became null on the horizon, but everywhere here it was time-like. It became space-like only the black hole region. Whereas here, already in the asymptotic region 1, this is already in the asymptotic region 1. The Killing vector field is becoming space-like. Okay, so it's really quite different from what we had before. Now, one of the things that we can do is to understand the properties of the Killing vector is to use the fact that you saw in your first homework problem that if I take the Killing vector field, any Killing vector field K, you saw that grad AKB, we just define this to be FAB up here. It's a 2 form because it is antisymmetric because of Killing vector. And you saw that in fact, if you have a vacuum equation, it implies that FAB satisfies Maxwell's equations. This then led us to define interesting conserved quantities like given Maxwell field. It's a fictitious mathematical Maxwell field. There is really no charge, but nonetheless it is defined by the symmetry, and therefore I can define conserved quantity. And then it turned out that the conserved quantity was mass after a sign. It was actually the mass up here in the short, in fact, K was taken to be T, and that you showed that in your homework problem. So this is really the Maxwell field, but now of course given a Maxwell field, you will also have a vector field K. So in our case, let's suppose for definiteness, K is equal to T. This is vector field d by dt that we have got, just for definiteness. Then we also have this vector field d by dt, and I got a Maxwell field. Now if you're given a vector field and a Maxwell field, usually with that vector field we take it to be timeline. We're just going to use here d by dt, even though it's not everywhere timeline. In the asymptotic region it is timeline. So we take this and we can decompose the Maxwell field into electric and magnetic parts. Right? This is the standard decomposition you learned in special relativity. This is giving you the instantaneous rest frame, if you like, and then we're taking the electric and magnetic part. So you can define EA to be just equal to FAB TB, and you can define BA. These are again, it's a mathematical construct, right? There's no physical charge there, but nonetheless, so I got this Maxwell field, I mean mathematical Maxwell field, and I get FA. And then similarly, BA to be equal to star FAB times TB, which is just equal to 1/2 epsilon ABCD. You know this, I'm just reminding you. So if you are given this, it's a very simple exercise, but I would like you to check that this is the case, that you all know that Maxwell field in 4 dimensions, it has 6 components, so 2 form. So 2 form the antisymmetric tensor in 4 dimensions has 6 components. And the electric and magnetic fields each has 3 components. So you would expect that in fact this electric and magnetic fields would actually have the same information as the full Maxwell field. And you are seeing this in special relativity. That's the case, that the Maxwell field can be expressed in terms of the electric and magnetic field. And indeed that is the case. You can write down FAB. In our case, with these definitions, you can write down FAB to be equal to twice TA EB. This is the electric part, which is proportional to there is a component up here, which has T component up here, if you like, upon the norm of the Killing field. So I'm going to write lambda to be equal to minus TA. So lambda is positive, plus epsilon ABCD times BC upon lambda. So it's very easy. All you have to do is to check that is this correct. Well, you just put T into it, see if you get electric field. This should go away, you should get electric field. You take its dual, plug T into it, and see that you get magnetic field. So this is an exercise for you to check that this is the case. So this is a simple expression for the Maxwell field in terms of electric and magnetic parts. Now, if you have the magnetic-like part up here, this magnetic part, BA, or just equal to 1/2 epsilon BCD times FCD, FCD was just equal to graph CTD, times TB, so I have TB graph CTD. This is a magnetic part. This in the geometry literature or in general relativity literature, this is called the twist of a vector field. This is called the twist of a vector field. And lambda is called the norm of the vector field. Norm of PA. This is called the twist of field. So this twist of the vector field, its reason is what you think it is, that namely the vector field is twisting, so there is some rotation. If in fact the magnetic part is not equal to 0, then the statement is that there is twist for this vector field. So then the statement is that the necessary, not only just for a Killing vector field, this definition can be given for any vector field. So for any vector field, if its twist is not equal to 0, then it fails to be a hypersurface orthogonal. So it's not perpendicular to any slices. Now, this is a little bit counterintuitive for the first people who are seeing it for the first time. So what exactly is happening here? So let's go back. Example, let's just go back to Minkowski space, and in fact we want just two-dimensional Minkowski space. And in two-dimensional Minkowski space, the reason I'm looking at two-dimensional Minkowski space is because I'm just interested in vector fields d by dt and d by d phi, if you like. So therefore, then I can consider actually that three-dimensional Minkowski space, because to have the vectors in two-dimensional Minkowski space, there's only one space direction, therefore there is no rotation. So I need three-dimensional Minkowski space, so space is two-dimensional, and I got a rotational Killing vector field. And then I got here, therefore, the vector field dA and the vector field phi. This is the time translation. So if you like, in the Cartesian chart, it's called components as 1, 0, 0, 0. And this is a rotation. So in the Cartesian charts, its components are, the t component is 0, x component is y component is minus x, z component is 0. So that's the rotational vector field that we will have up here. So it's three-dimensional Minkowski space. So what do the orbits of t look like? Well, they just look like that. What do the orbits of phi look like? Well, they're space-like, and they look like the circles, right? So think of this as being three-dimensional Minkowski space. So think of this as being time rather than space. Then I got d by dt Killing vector field, and I got a rotation Killing field up here, right? But now supposing I actually take a linear combination of them. So I define the vector field Ka to be equal to Ta plus omega times phi a. And for the moment, let's suppose omega is actually constant. Then this vector field, Ta plus omega phi a, since I'm just taking two Killing vector fields and adding, I'm taking a linear combination with constant coefficients, this is again a Killing field in Minkowski space, because you can just take this lead drags the metric, this lead drags the metric, therefore this lead drags the metric because omega is constant. So it's a Killing vector field in Minkowski space. And what do its orbits look like? Well, its orbits look like that, helical. So if an observer were to follow the integral curves of this vector field, observer relative unit, but if I have forward velocity to be equal to Ka upon K dot K, and I want the observer to be timeline. So therefore, if I were to take the observer to follow this, if I wanted this observer to be actually following this whole line up here, then actually this observer is going to be rotating. So in space-time, the observer is going like that, helically. So if I project its motion on a constant time surface, then it's just going on a circle. It's going on a circle with angular velocity omega. So I'm just translating the obvious trivial facts about rotational motion in Euclidean space into space-time language in Minkowski space. Circular motion with angular velocity. These kind of considerations are important for your homework problem, where notion of angular velocity and so on that comes up. So this is what is happening. And then this vector field, so this is an exercise, not a homework problem, but it's very trivial. You can calculate the twist of this vector field Ka. If you calculate the twist of Ta, it is very trivial, it's 0. Calculate the twist of phi, that is 0. This vector field Ta is of course hyperspace orthogonal, right? And is perpendicular to it. Phi is also hyperspace orthogonal because its orbits are just this. I can just take a section from the origin going out, phi equal to constant surface, and it's perpendicular to that phi equal to constant surface, not very profound. So each of them are hyperspace orthogonal, but this one is not. Not hyperspace orthogonal. And the non-hyperspace orthogonality up here is going to be related to this omega. If omega equal to 0, of course the hyperspace is orthogonal. If omega is not equal to 0, then it is not hyperspace orthogonal. So as soon as there is rotational motion up here, the vector field fails to be hyperspace orthogonal. Now in our case, it's a funny thing that is happening, because in our case we've got a vector field T by dt, which is our vector field TA. And the point is that this TA itself is not hypersurface orthogonal. Right? So it's this TA which is going to look like that. Right? And now in Minkowski space, if I take this vector field in Minkowski space, if I went out very far away, then the norm of this phi, remember that phi norm of the phi vector field is r squared sine squared theta. So this norm is going to grow, right? As r squared, its norm is going to grow. Whereas the norm of this vector field is just -1. So its norm is constant. So at infinity, the norm of this vector field is going to be dominated by the norm of phi. So the vector field would be actually space-like, this phi up here. And therefore, this vector field is actually space-like. So it's twisting, but it is time-like only near the origin, some open region, and then far away from it, it actually becomes space-like. But again, because we have got curvature, you can interpolate. The vector field can be just time translation out at infinity, and as you come in, so it's time-like here. And still, as you come in, it becomes more and more like TA plus omega phi a, so there is actually more and more rotation. And this is possible again because there is curvature in between. We saw this already in the case of the Schwarzschild, not this phenomena, but a similar phenomena. In Schwarzschild space-time out at infinity, the vector field looked like a time translation, but near the horizon, it looked like a boost. In Minkowski space, that can't happen. If it is time translation at infinity, that killing vector field is going to be time translation everywhere. If it is boost at infinity, that vector field is going to look like boost at Minkowski, at infinity of Minkowski space. So here what is happening is that this d by dt vector field looks like this TA, if you like, out at infinity, and yet it looks like TA plus omega phi a, Minkowski TA plus omega phi a. So maybe I should call it T naught. Let's put it here, T naught and phi naught for Minkowski space. And therefore, this vector field is going to look like, at infinity, this vector field looks like d by dt, but in the interior space-time, it looks like, and this is the reason why one says that in Kerr space-time, there is dragging of inertial frames. So there is a rotation or dragging. So one of the homework problems asks you to calculate actually the twist of this vector field d by dt, and you can see that that twist is going to be related to the dt d phi term. If dt d phi term were not here, the vector field will be orthogonal to grad a t, and therefore it's perpendicular to grad a t, and therefore it is orthogonal to t equal to constant surfaces. It is this term that spoils the hypersurface orthogonality of d by dt, and that you will see explicitly by calculating the twist. You will see that in the Kerr space-time, the homework problem, you will see that this twist goes to 0 at infinity, but is important, it's non-trivial in the interior. So if you don't want to tie down your notions to coordinates, people often talk about dragging of inertial frames and so on. And I always have a little bit skeptical about that because I don't know what an inertial frame is in Kerr space-times and real manifolds. So there is this heuristic idea that is translated using some coordinates, but the invariant meaning of that is just that you have got a non-trivial twist, therefore the killing vector field has a rotation in it, but out at infinity the twist goes to 0, therefore out at infinity it really looks like a time translation. So, therefore, our vector field TA is quite different from the so TA different from the one in Schwarzschild. Of course, for a not equal to 0. So for a not equal to 0 and a not equal to 0, there's quite some difference. And how do you sort of see this difference? So the first thing is that it is, we already saw that this TA in curve is space-like near the horizon. Near r equal to the r horizon or r equal to r plus, it is actually space-like, even in the region 1, in the asymptotic region 1. And the second thing is that TA has non-zero twist. So you can ask, well, okay, it has non-zero twist. Is there some vector field that I can construct, natural vector field, which would be actually hyperspace orthogonal for this chart? And the answer is yes. You can just consider the vector field I think in a homework problem I call alpha A. In literature it's often called eta A, but we have been using eta for geodesic vector field. I didn't want to confuse the two, so let's call it alpha A. So consider this vector field of alpha A to be equal to TA minus T dot phi divided by phi dot phi times phi A. Why did I choose this coefficient? Well, just to make alpha A phi A equal to 0. So this vector field is perpendicular to the rotational killing vector field phi A. So when I take this vector field, if you like, for this vector field, this dt d phi kind of term should not matter because heuristically, because it's perpendicular to phi equal to 0. And you can check, these are again homework problem, that this vector field is hyperspace orthogonal. And in fact, I asked you to what surfaces is it orthogonal to. So this vector field is hyperspace orthogonal. And the easiest way to do is to lower its index and show that this is equal to f times grad A of g, where f is some function and g is some function, and this vector field is always orthogonal to g equal to constant surfaces. If you've got a vector field like that, if a vector field is orthogonal, grad A g is of course orthogonal to g equal to constant, because it is perpendicular. But if I just multiply it by some function, then it's still orthogonal. It's just that its norm is, modulated by this f up here. So that's what you have to do in the homework problem. You have to lower the index and quickly check that in fact it is of this case. And the question is, which surfaces is orthogonal? Where is going to be orthogonal to g equal to constant surfaces? So you can figure out what that surface is. So because it is perpendicular to phi, if an observer were actually following this vector field, of course it's not going to be geodesic in general because this vector field is not geodesic. So observer, first of all, UA, if I got an observer UA, or time like test particle and observer UA, so that UA, if it were to follow this vector field, UA is equal to alpha A upon alpha dot alpha. You can also check that this vector field alpha is always time-like outside the horizon. So we saw here these two things. It is not, this vector field has a twist. This alpha does not have a twist. This vector field was space-like somewhere. It was time-like at infinity, but space-like somewhere. And this vector field, on the other hand, is actually going to be time-like everywhere. At infinity, these two vector fields agree with each other. I told you that at infinity, the rotational killing vector field is not blows up, right? But I got here phi dot phi here. So t dot phi goes to 0, phi dot phi goes to 0 quite fast. The norm of phi a goes up, but this is square of the norm. Therefore, this term goes to 0. So at infinity, I should just write here, as r goes to infinity, in fact, alpha a does go to TA, but in the in-between region, it is not TA. But notice that this, whereas here I just chose this to be a constant, now this object up here, we can call omega, this is a function, not a constant. So this depends because t dot phi and phi dot phi. T dot phi is this, except for a factor of 2, it is this, and phi dot phi is just this. Right? Then now I'm going back to GAB phi. You can see it depends on r and theta everywhere, so it's not a it's a function of r and theta. So omega is omega of r and theta. It is not constant up here. But you'll find that on the horizon, this in fact is constant. Omega at r equal to r plus is equal to constant. So a priori it could not depend on theta, but does not depend on theta. So again, this is implicit in your exercise, in your homework, but you can check it independently that this omega, t dot phi upon phi dot phi, is actually constant. Now, if I take an observer, which is actually following the whirl line of this vector field alpha, so its forward velocity is this, then the angular momentum that this observer of this observer is going to be equal to, so let me not call capital J, let me call it little j, angular momentum of this trajectory instantaneously at any instant of time is going to be given by UA times the angular momentum phi A. But we just saw alpha A phi equal to 0, alpha A phi equal to 0, therefore I is going to get 0. So these observers, if you manage to follow the whirl lines of this observer, you will need a rocket ship and so on because this observer has acceleration. But if you manage to follow the whirl line of this observer, then you are staying still. Then you are not rotating. So your angular momentum is 0. So these are often called zero angular momentum observer or ZAMOs. So these are zero angular momentum observers. On the other hand, in the region at least where t is time-like, if you are going to follow the Killing vector field, in the asymptotic region, for long asymptotic region, this actually is true. So if you're going to follow these observers, follow the whirl line, so in other words, again, you'll need a rocket ship because you are remaining stationary. You're not seeing the geometry. If you did not have a rocket ship, you'll fall into the black hole. So the geodesic will fall in the black hole. On the other hand, or if you had a so it will fall into the black hole. And then the statement is that on the other hand, if you have got a rocket and you actually follow this angular momentum, then for this observer, the angular momentum is not 0. So for this observer, Ja is equal to Ta upon minus T dot T times phi A. And that is not 0, and that is just equal to, you just calculate what it is, and you will see it is not 0. So it's just this times phi, so I'm going to get T dot phi here, and I'm going to get phi dot phi here. Sorry, what happened here? So I added Ta times phi A. So if I take, Ta times phi, not alpha, but Ta times phi A, then this is just equal to T dot phi. This is equal to T dot phi minus T dot T. T dot phi is this term again, except for a factor of 2. T dot T is this term, and therefore that term is not equal to 0. As you go out to infinity, this goes to 0. So as you go out to infinity, these ZAMOs these stationary killing observers following the stationary the orbits of the stationary killing field, the observers which somehow manage to remain stationary in the space-time, their angular momentum at infinity will be 0, but as you come into space-time, it is not equal to 0. So, therefore, for an observer, for an observer who is following this, I'm following this T up here, thus, since Ta is equal to alpha A plus omega theta r times phi A, we can see that this Ta with respect to non-rotating observer, with respect to ZAMOs, which are non-rotating, this TA is rotating with angular velocity omega. But of course, this angular velocity depends on theta and r in general. And now at the horizon, this heuristics will not work because at the horizon, in fact, TA is spacelike. But nonetheless, I can calculate what the angular velocity is at the horizon. And I look at omega as r plus, and as I say, is constant. And this is just written as omega h. This is constant. Angular velocity at the horizon. And this is often called the angular velocity of the horizon. So there is a very interesting interplay between geometry and physics. Geometrically, we just have these vector fields which happen to be not hypersurface orthogonal. Such vector fields are very common. Almost every vector field is not hypersurface orthogonal. But the interesting thing is that the vector field, which looks like a time translation isometry at infinity, inside space-time is not hypersurface orthogonal. Therefore, stationary observers would always look like would always be rotating inside. And then the last part of this curved space-time is the following. I already said that the Killing vector field d by dt is actually space-like on the horizon. Therefore, the Killing vector field, let's step back. In Schwarzschild space-time, the Killing vector field was actually time-like at infinity, came in, and at the horizon become null, and it was a null generator of the horizon, right? It was a null vector field at the horizon. And therefore, as we saw, the horizon was actually a Killing horizon for the time translation at infinity. But here this is not going to be the case because we already saw, I already asked you to check, that in fact the Killing vector field TA, the norm, actually becomes positive near the horizon. That means that the Killing vector field must store over somewhere else. Remember that where the Killing vector field becomes null is the infinite redshift surface, because the redshift has to do the behavior of the Killing vector field, has to do the norm of the Killing vector field. In Schwarzschild case, the infinite redshift surface is the horizon, but here it is not. So where does the Killing vector field become TA? Become null. If it is time-like at infinity, right? If it is time-like at infinity and space-like near the horizon, then somewhere in between it must turn over and become null. If you have a time-like vector field, it cannot become space-like, it's a smooth vector field, unless it becomes null somewhere. And you can easily see where it becomes null. So we just solve for the fact that there is norma, the norm of the Killing vector field, lambda is equal to 0. This is where the norm of the Killing field, so lambda is equal to minus TA, 0. I just erased, unfortunately, so just had the formula for here for the dt squared, so the coefficient of dt squared becoming 0. And you see that you have got roots. So if I were to plot the R line, then, so in this various diagrams, I'm just looking at t equal to constant surface, and I'm looking at R line up here. So what happens is that you've got a horizon, or this is the horizon is R equal to R plus, this is the horizon, outer horizon. But in fact, you've got a place outside there where R is equal to M. So I should write R plus is equal to M plus square root of M squared minus A squared. Here, M plus square root of M squared minus A squared cos theta. And another root where it becomes null again is inside the outer horizon, and that is R equal to R minus, is equal to R equal to M minus the other root, M squared minus A squared cos squared theta. So if you are coming from infinity, the Killing vector field is all time-like here, it becomes null here, becomes space-like. Space-like here, so this is time-like, this becomes null, and then space-like up here. So it's space-like around the horizon, and space-like remains space-like, and then turns again null somewhere inside. So we're really interested mostly in this region. So again, if I were to draw this picture, then I would find that, in fact, what would happen is that there is a region. So I can draw, for example, r equal to r plus, first of all. So this is the region r equal to r. This is the surface r equal to r plus. I'm drawing this surface in a constant t plane. So this is r equal to r plus. It's not a circle. It's actually it's a not a geometric circle, but it's a coordinate circle. R is a constant up here. R is constant up here. But then here, when it becomes null, that surface is going to look like, because of the cos theta thing here, that surface is going to touch here, but here is going to become fat. Here is going to touch. It's going to become fat. So what I'm doing is r theta, right? So this is going to be equal to theta equal to 0, theta equal to pi. So it's going to touch here. So if you like, in the three-dimensional picture, I have to rotate it along the phi axis. So this will be generated in phi axis. I have to rotate it along phi axis. So the statement is up here that I'm just looking at I got this sphere, and I'm looking at the cross section of this sphere, and that is what that. So in this region, and also inside, but as far as region 1 is concerned, in this region, the Killing vector field is space-like. This is called ergo region. Now, I had to quit, but what happens with the ergo region is that completely new process is possible now. It is possible to throw in particles which are positive energy. They can decay into two particles. One has positive energy and the other has negative energy, and the positive energy particle can come out. This was realized by Penrose early on. So you can actually extract the energy out of the black hole, out of the rotating black hole. What you're doing is you're extracting the rotational energy. So you're going to slow down by this process. This is called the Penrose process. So the last thing we have to do tomorrow, on Wednesday, is the Penrose process. A little bit of our super radiance, and then we'll be done with this, and we'll start the more interesting topic, which has to do with, to me, it's more interesting topic, which has to do with non-stationary black holes. And you will see again that the stationary paradigm, which had been around for a very long time, and 99% of work in black holes is done on stationary black holes or black holes, analytical work, stationary black hole or black holes, perturbations around stationary black holes. And that is just not sufficient at all if you want to do really non-stationary dynamical black holes, such as the ones LIGO saw, which actually merged and formed a full black hole. So how do you describe that? That is what we're going to see in the next 3 lectures. Okay. Thank you.